Greetings, folks. Welcome. The practice of statistical inference is using information from a sample of data to say something about a larger population. One application of statistical inference is to use information from a sample to estimate a population mean. For example, you might want to try to estimate the average age of all people who visit Disney World. Of course, oh wait, I'm actually wearing my Mickey Mouse sweatshirt. I didn't even make the connection until I just said that. That's pretty sweet. Hi, folks. How you doing? Okay. Anyway, so let me get back into lecturing mode here. So you might want to estimate the average age of all people who visit Disney World. So unless you are Mickey Mouse himself, you're never going to have access to everyone who goes to Disney World. So instead, you'll have to rely on a sample of data. So to estimate a population mean, you first calculate a sample mean and then put a margin of error around it. So here's the notation you see. Mu, that's a population mean, equals x bar, which is a sample mean, plus or minus the margin of error. An example of what this might look like is the statement you see here. Average household income in Maine was $73,598, plus or minus a margin of error of $1,747. The margin of error accounts for the fact that you just have a sample of data, and if you were to have different samples of data, you'd likely get a different value for average household income. The margin of error is determined by the confidence level, which you set as the researcher, and the standard error of the sampling distribution. So there are really a couple factors that affect the size of the margin of error. So you see, we've got it written down here as a little formula. Margin of error equals T subscript alpha divided by 2. This is a t value that's based on the confidence level that you set as a researcher, and I'll show you in a second what that means, multiplied by s divided by the square root of n. This should look familiar because this is the standard error of the sampling distribution. So s is the standard deviation of the sample, and then that n, or the square root of n, is the square root of the sample size that you might take. So you pick a confidence level based on how certain you want to be that the actual range, the confidence interval that you report, includes the true population mean. So for example, a 99% confidence level means that you are 99% certain that the confidence interval that you calculate will include the true population mean. If you decide you want to use a 90% confidence level, then you're saying that you are going to be 90% certain that the confidence interval that you calculate will include the true population mean. So if you want to be more certain that your interval captures the true population mean, you ultimately need a larger interval. So a confidence interval that's done at the 99% level will actually be a larger interval than a confidence interval that's done, say, at the 90% confidence level. Here are the steps that you would follow to find the t-value that you'd use to calculate the margin of error. First, you start from the confidence level. Again, this is something that you set as a researcher. You could do a 99% confidence interval, a 95, a 90, again, whatever you want to do. So you take that value and you subtract it from 1. So let's say you're doing a 90% confidence interval. You would take 1 minus 90%, and what's left is 10%. So that's your alpha. So alpha would be 1 minus the confidence level that you set. Then you calculate alpha divided by 2. So let's say you're doing a 90% confidence interval. 1 minus 90% gives you an alpha of 10%. 10% divided by 2 gives you 5%. Then you find the t-score that corresponds with that value, that alpha divided by 2, and you use n minus 1 degrees of freedom, where, of course, n is your sample size. So suppose you want to estimate a 90% confidence level. So your alpha is 0.10 because that's 1 minus the confidence level that you set. You calculate alpha divided by 2, which is 5%. Then you need to go find the t-score that corresponds with 5% at the upper tail of the distribution using 50 degrees of freedom. And that's because the degrees of freedom would be the sample size minus 1. So here's the t-distribution with 50 degrees of freedom. You can see 5% in the upper tail. There's also 5% in the bottom tail. So what's left in the middle is 90%. So you see that middle part of the distribution that accounts for 90% of the t-distribution. That's really sort of the confidence interval that you're estimating. So if you want a 90% confidence interval, you're really, again, looking for the t-value that corresponds with both the top 5 and the bottom 5% of your distribution. So here's your trusty t-distribution table. Of course, it shows the upper tail for a given degrees of freedom. So in the first column, we have degrees of freedom. You see 45, 46, etc. You want to go down to 50 degrees of freedom because you have a sample size of 51. Because you're doing a 90% confidence interval, your alpha is 10%. Divide alpha by 2, you get 5%. So you're looking for the 5% in the upper tail. And we see here that the t-statistic that corresponds with the 5% in the tails with 50 degrees of freedom is 1.676. So now you can actually go back to your t-distribution with 50 degrees of freedom. You can actually fill in the values. So you see the value of 1.676 corresponds with the top 5%, or the 5% in the right tail, and a t-statistic of minus 1.676 corresponds with the bottom 5%. That's because your t-distribution is symmetric. Now, if you want to use information from a sample to calculate a population mean value, and you've decided you want to do a 90% confidence interval with a sample size of 51, which gives you 50 degrees of freedom, this is a formula that you'd use. Mu, again, that's the population mean, equals x bar. This is a sample mean. This is actually something you can go out and calculate. If you just collect information on 51 people, you can put that information, say, into Microsoft Excel and calculate a sample mean, plus or minus 1.676. That's the t-statistic that we found. Again, just a second ago, we looked at the t-table, and we found that if you have the top 5% and the bottom 5% of a distribution with 50 degrees of freedom, it's 1.676 for the t-statistic. You multiply that by the standard error of the sampling distribution, which is a standard deviation of the sample. This is something you can calculate. And if you collected data on a sample of 51 people, that's information you could put into Microsoft Excel or in other statistical software and calculate a standard deviation and divide that by the square root of the sample size, which is the square root of 51. In a different video, we'll actually do some calculations to find sample means and standard deviations and be able to complete the confidence interval.